Can someone please confirm to me that you can see the PowerPoint and you can hear me?
Yes.
Perfect. Thanks. All right. So hopefully we're going to knock out chapter 2 today and get started on chapter 3. We just need to finish talking about water. And remember, I guess the biggest thing we've said so far about water, because everything else we say pretty much boils down to this, is that water is a polar molecule, right? So the oxygen end is a little bit more negative than the hydrogen end because it's a little bit more positive. And because of that, there's these slight attraction between water molecules. Not as much as an ionic attraction because it's not fully charged, but a slight attraction. And that makes, those polar molecules make these hydrogen bonds. And pretty much everything we talk about in this is due to the hydrogen bonds. Whoops. So the last thing we talked about was the cohesion of water. And basically the book example was, how do we get water from a root all the way up to the tippy top of the tree? And again, it was the cohesion of water, because when one molecule maybe evaporates, for example, then it basically pulls it like a chain and everything just moves up. But anyway, let's talk about how water moderates temperature. So water has a very strong resistance to temperature change than most other substances. So for example, when you're next to the coast, if you've ever gone to the beach, the water temperature doesn't change drastically. I remember I went down to Cherry Grove Beach for New Year's, and when we got there, it was a relatively warm day, but the water was still in the 50s. It was pretty cold. But then I think sometime when we were there, the air temperature dropped down to maybe, I think, the 40s, but yet the water was still in the 50s because water, it's harder to change the temperature of water. Why does this happen? It happens, and this is a little bit less important as far as the exam is concerned, but hopefully if you understand why it happens, it'll be easy to remember that it happens. So what happens is when water is heated, first thing it has to do is disrupt these hydrogen bonds, which makes, let me back up. Let me say this too. Before I even tell you what this is, let's talk about what heat is, what temperature is. If I were to say right now, well, my room's getting hotter, the room that I'm in, the temperature is increasing. What I mean by that is that the air molecules in the air, they're moving around faster. That's what heating up means at the molecular level. Cooling down means the molecules are moving slower. So remember, I'm going to try to draw this. The water molecules, because they're polar and because they have these attractions to each other. So even if it's, whether it's water molecules in the air as vapor or water molecules in the water, liquid form, it's still going to do this, right? So they're all attracted to each other. So I've just drawn here 2 water molecules attracted to each other, but imagine many, many more. Anyway, the point is, as things start to heat up, these molecules are moving more, right? Maybe they're trying to rotate, maybe they're vibrating, whatever the case may be, they're moving. And the more they move, the hotter they get, or the hotter they get, the more they move, however you want to look at it. So what happens is they can't move around too much because they have these hydrogen bonds, right? Those hydrogens are attracted to those oxygens. So imagine if I told you guys, if we were in person right now instead of online, if I told you all to stand up and hold hands. And then I said, all right, now I want you guys to jiggle around and dance and things like that, right? At first, you guys just be jiggling around, but you can't move too far because you're holding each other's hands. And then imagine I said, all right, now I really, really want you to just move around so much that you guys just can't hold on to hands anymore because you're too much energy, right? And that's what would happen. Eventually, if you really jerked around a lot, eventually you would lose those bonds, right? You couldn't hold on to the hands anymore. So then you could really start spinning around the room and moving around any way you want. Same thing happens with water, right? Yeah. For a long time, when you apply heat to the water, it's moving up a little bit, but it still has those hydrogen bonds. So it's not moving around that much. And it doesn't move around a lot until you can break those hydrogen bonds. So again, I just want to make sure you understand it. Well, I want you to understand it, but for the exam, the most important thing you need to know is that it takes a lot of energy to change the temperature of water. And hopefully with me explaining why, that'll help you remember that it does. And then we talk about cooling. So when cooling, hydrogen bonds form. So it's basically just the opposite of what I just told you, because we're talking about getting cooler instead of getting warmer. So those water molecules that were just willy-nilly going all over the place, once you cooled them enough, then those hydrogen bonds reform, and that process actually releases heat. So again, that tells you why, a good comparison would be a coastal area where the water temperature does not change nearly as quickly as the air temperature. And another thing, and this is a little bit harder to visualize sometimes, it makes it harder for even the air temperature around the coastal area to change because there's all that, that body of water is like this beacon of heat, depending, or coolness, depending on the situation. So yeah. So yeah, water moderates temperatures. That's the key thing here. That's what you need to know. And that's not trivial because this allows temperatures to stay within the limits that permit life. Basically, without water on Earth and without the greenhouse effect, which we'll talk about later, we just wouldn't have life as we know it. There would definitely be some things that could survive, but it wouldn't be us. I mean, it would be probably maybe now for a little bit we could have the technology to survive it, but we certainly wouldn't have been evolved and wouldn't be here to begin with if the temperatures were not where they are. So again, if you have water, even in our area when we have rivers going through us through our area and we have humidity in the air, right? So what happens is during the day, the sun's heating all that water up again, including in the air, so it gets nice and warm. But then at night, or we could also compare this from summer to winter, but either way, the water's storing all that heat during the day or during the summer, and then in the colder periods, whether it be night or winter, there's still some of that heat um, stored basically, and it's getting released. So that's why you see less drastic temperature changes, generally speaking, in areas that have water, which is unlike most deserts, right? Deserts will get really hot during the day because there's no water to absorb all that heat. And then at night, it'll get really cool because there's no water then to release that heat. So, any questions about how or that way that water moderates temperatures? All right. The next way water moderates temperatures is basically through sweating, and I'm sure you guys knew that. When you get hot, you sweat, um, and then there you go. That cools you off. I guess I'll go through this really quickly. No, well, yeah, okay. So again, water moderates temperatures on Earth. So generally speaking, these areas that are farther away from water, right, towards the middle of continents, generally speaking, they have more drastic temperature changes from season to season. And generally speaking, these coastal areas don't. Another interesting thing is, here's where we are, about right there, that dot that I'm making. And here's where England is. London's right about there. And you can see there's a big difference, right? England, that's up near Canada area. That's up near either the tip of Alaska or, near Vancouver. So it's pretty far north. However, its climate is a lot like ours because we have all this water at the equator getting heated up by the sun, and then it moves forward or moves up, moves north because of the currents. As it's moving up, it still has some heat and it's still giving off some heat. Then it hits that continent and it comes back down. And so you have all these areas, coastal areas up here that have a relatively warm climate because of the water. But that's just an example. Anyway, any questions about how water moderates temperatures or why it's important? All right, here's one that's a little less intuitive. So we all know ice floats, but did you know that that was biologically significant? And here we go. Let's talk about that. One thing you need to know, at least for the study guide, maybe for the exam, is why ice floats. And what happens is when the water molecules get cold enough, they actually move farther apart. Um, and that's not a normal thing. Usually, when things get colder, they have less energy, so those molecules are moving around less, like I told you earlier. So they get, closer together. And eventually, water gets to a point where it doesn't do that. It actually gets farther apart. And because things are farther apart, that means it's less dense, and that's what makes it float. So again, that's one thing you need to know. Ice floats because it is less dense than the liquid it is in. And why does that happen? Why is it less dense? Well, because when the water molecules get cold enough, they move farther apart. Any questions about that so far? All right, here's a picture of what I'm talking about. And I love this picture because this kind of goes back to what I was talking about earlier, which I was trying to draw. You can see these water molecules kind of vibrating and jostling around because there's some temperature, right? There is some energy in there, yet there's still those hydrogen bonds. But of course, in this case, we're talking about freezing, not heating. But anyway, That being said, you can see here on the right, this is what happens. They eventually get cold enough, they stop jostling around, and they just get this rigid structure. And in this rigid structure, the water molecules happen to be farther apart, and they're less dense. Like, look at this picture on the left versus this picture on the right. You can see there's many more water molecules on the left than there are on the right, because again, it's less dense, and that's what makes it float. Any questions? All right. So let's talk about why that's important biologically. It seems pretty trivial unless you think about why it's important. Because, well, one of the reasons is as bodies of water cool down, obviously, if they get cold enough, you have a layer of ice on top. And I know this might sound weird, but that's essentially a blanket for the water. And I know that sounds weird because because when you think of a blanket, you don't think of ice, right? You don't think of something cold. But in this case, it is, because it's all relative. So if you have this body of water, once it starts getting cold enough, then you get this chunk of ice on top. So even if the air temperature gets down to like negative, I don't know, I'm just making a number up, negative 20 degrees Celsius, like it might in the Arctic area, it might get cold, really, really cold, but there's this blanket here. So the water down below, it's staying relatively warm. It's staying above the freezing level. Yeah, a little bit of it that's coming in contact with the ice is going to be really cold, and it might even add to the ice thickness. But generally speaking, that blanket, that sheet of ice, is basically protecting the water. So without that, basically all the bodies of water on Earth, depending on where they are, they would just freeze solid. In which case, most things would die, right? Like these seals, they're really cool. They're really fine with these really cold water temperatures, but they can't live in a sheet of ice, right? So without the fact that ice floats and insulates, then things just couldn't persist. Any questions about that? All right. Let's talk about water as the solvent of life. First thing you need to know if we're going to talk about that is what a solvent is. So there's a few words you need to understand if we're going to have this discussion about a solvent. The first word you need to know is what a solution is. Now, everything I'm about to tell you on this slide is going to be coming back again next in the next unit. So you'll have it on this exam and probably have it on the next exam too. So as simple as these words are, they are important. So make sure you understand them. Anyway, a solution. A solution is a liquid with a homogeneous mixture of two or more substances. What do I mean by homogeneous? Basically, by looking at it with your naked eye, it just looks like one liquid, one substance, right? So if you look at a glass of tea, it just looks like tea. However, if you were to put ice in it, a glass of iced tea, that would be not a homogeneous mixture, right? You could see with your eyeballs, oh, there's the tea, there's the ice, right? Or if you were to Kool-Aid, I don't know, maybe that's even what this cat's got going right there. If you were to mix up some Kool-Aid, if you did it properly, it just looks like Kool-Aid. It's not like through the naked eye you can say, well, there's the water molecules and there's the Kool-Aid molecules, right? It doesn't work that way. So that's what a solution is. So if we have these substances that are in the solution, what do we call them? Those substances are called the solute. So again, maybe the Kool-Aid or the molecules of tea, right? The solute is the stuff in a solution. What dissolves the stuff, that is called a solvent. So you need to know those three words, know how they're related to each other. You should be able to use them in a sentence or in a description, right? To make a solution, we dissolve solutes in solvent. So moving back to this discussion about water, when water is the solvent, it is called an aqueous solution. Now, as far as the exam is concerned, and even the semester, I think the most important stuff is this bullet point right here. No solution, solvent, solute. Excuse me. Yes, it's an aqueous solution, but I'm probably not going to make that differentiation throughout the semester. Any questions about this? All right. So now that we know what a solute is and a solvent and a solution, we can move forward. Your book points out that water can dissolve a variety of solutes, and it provides a medium for chemical reactions. And the first word for attendance is going to be that one right there. So you can see it. I'm even going to write ATT for attendance. I would write the whole thing, but it's a pain. So yeah, I'm going to change it up a little bit. I'm not going to say it. I'm going to show it, because again, the purpose of these words is to make sure people are paying attention. So anyway, yeah, that's the first word for attendance. I'll even put number 1 right there. So yeah, water can dissolve a variety of solutes. That's important because you need chemical reactions. And again, like we said at the beginning of this chapter, basically everything that happens in biology can be boiled down to chemistry. So without these chemical reactions, we don't have life. Your book gives an example here. When water dissolves salt, each ion, remember the salt ions, because it has sodium chloride, one's positive, one's negative, each one becomes surrounded by the oppositely charged regions of the water molecule. So again, these water molecules are, these water molecules are polar, right? Because these hydrogens are partially positive. These oxygens are partially negative. So when you mix them with salt, which is fully positive and fully negative, and that's what happens. You can see this negative chloride is being pulled away and surrounded by these positive hydrogens. This positive sodium is being surrounded by these negative oxygens. So here's why that's important. Imagine if I gave you a huge brick, like hundreds of Legos, and the Legos were green and purple, right? And I said, all right, I want you, and I gave that to you, and I said, can you please build me, I don't know, a green building? What's the first thing you would do if I gave you a big brick of all these green and purple Legos attached to each other? And this isn't this is not a rhetorical. Can someone answer me? What would be the first thing you would do if I were to give you this big brick?
Pull them apart.
Yeah, pull them apart. And that's the same in your cells. So your cells need sodium. Your cells need chloride. But when you give them sodium chloride, you have not given them exactly what they need. That in itself is not what they need. They need sodium for some things. They need sodium chloride for others. So you need the water to be able to dissolve them so they can be used in their respective chemical reactions. Excuse me. Any questions about this? All right. Here's another one. For those of you who had lab on Monday, this is a little bit of a review for you. So you might be able to say that's an advantage. But then again, for those of you who have lab today, when you have lab, it will be a review for you. So maybe that's the advantage. I don't know. But here we go. Let's talk about acids, bases, and pH. First of all, you need to know what an acid is. And there's actually quite a few different definitions. But in this class, we defined acids as a compound that releases hydrogen ions. So basically, you should associate H plus with acid. The more H pluses there are in a solution, the more acidic it is. Does anybody have any questions about that concept? Well, and to remind you, you might be wondering, H plus, how is that a hydrogen ion? Well, remember, a hydrogen is that one proton. Yeah, there we go. And that one electron, right? So if you were to get rid of that one electron, get rid of that, then the only thing you're left with when you get rid of the electron to make a hydrogen ion is just that one proton. So that's what this is, H plus. Anyway, that's what an acid is. Whoops. I wonder if I can erase this. Yay, look at that. Okay. So anything, and then, all right, there's two different ways that we are going to describe bases. A base, first of all, is anything that accepts those H plus ions. So again, an acid gives off those H plus ions, and a base accepts them. So again, the more H plus ions you have, hydrogen ions, then the more acidic it is. The less H plus ions, the fewer H plus ions you have, the more basic it is. So anyway, yes, if it removes those from the solution, it is called a base. Some of these bases do this by releasing their own ions. Specifically, they release hydroxide ions, which, are basically the opposite of the hydrogen ions that we looked at up there, right? Those are positive, these are negative. And what happens is these two things can form up or combine to form water, right? H2O, right? 2 hydrogens, 1 oxygen. So again, the important thing you understand, especially for the exam, is what an acid is and what a base is, and all the different ways to describe it. So on one end, you have very acidic which is the H plus. On the other end, you have more basic, which is OH minus. So again, there's so many ways to describe the same thing. If we're going from here this way, right? If we're changing the pH and going that way, we could say it's becoming less acidic. We could say it's becoming more basic. We could say we are having fewer H plus ions. We could say we're having more OH minus ions. You see what I'm saying? Make sure not only do you know what's on here, but make sure you understand that there's different ways we can describe the same thing in this conversation. Because for the exam, you'll need to be able to describe them in those different ways, or more accurately, you'll be able to recognize them as you read them in the exam. Because I might write it one way or I might write it the other. So, any questions about that so far? All right. So it is the pH scale that describes this. I just showed you, going from H plus to OH minus, and that is actually what I didn't tell you when I drew that, was that is something called a pH scale, right? A pH scale describes the acidity. What is the acidity? Again, like I've already said, it is the measure of the concentration of H plus ions in the solution. So again, the more H plus ions it has, the more acidic it is, the less basic it is. And here's another thing you need to know for the exam. You need to know that 0 is the most acidic and 14 is the most basic. And obviously because of that, right in the middle of 0 and 14 is 7. So 17 is neutral. Excuse me, 7 is neutral. Another very important thing that you need to know, and I'm going to elaborate on this on the next slide, but each unit, every full step in the pH scale is a 10 times change in concentration. So when we talk about this on the next slide, please make sure you're paying attention, because this is the part that gets people on the exam. Well, not this next slide, but it's coming up. This is just a visualization of what we're talking about. Here's a basic solution. It's basic because you can see it has more of these OH minus than these H pluses. Here's an acidic solution because it has more of the H pluses. And here's a neutral solution because it has the same amount, right? Equal amounts of OH minus and H plus. All right, here it is. Here's what you need to know. Obviously, you don't need to memorize this. So there'll be no questions where I'm like, what is the pH of household ammonia, right? I'm not going to ask you that. If I did, I would give you this picture and then say, what is the pH of household ammonia? And you would just look and say 12. All right. So that's the first thing you need to know, is that you don't have to memorize this. So the second word for attendance is going to be that, ammonia. Anyway, moving forward. Oh yeah. So a question that you might get on the exam that you definitely will get in lab and in the study guide is I'll give you a picture like this, where I'll give you the necessary information, and I'll say, how much of a change is it, for example, to go from pure water to black coffee? So let's call pure water is 7. Let's call black coffee 5. So the most easy way to describe it is say, it's 2 steps, right? We're going 7 to 6 to 5, right? So that's 2 steps in the pH scale. And you'll never explain it that way. That's too simple. Another way you could say it, and more specifically, is it's 2 steps more acidic, right? Because you've gone down the pH scale. So you would say black coffee is 2 steps more acidic than pure water. However, even that's too simple. We're not going to use that either. Instead, like I said earlier, each step is a times 10, not 10, but a times 10 in magnitude. So when you go 7 to 6, that's 10. And then if you go 7 to 6 to 5, that's, you multiply that by 10 again. So that's 100. So 1 step is 10, 2 steps is 100, 3 steps is 1,000, 4 steps is 10,000, 5 steps is 100,000, 6 steps is 1,000,000, so on and so forth. So that part you definitely need to know. That's the first part. Remember, each step is a time 10. So one of the wrong options you would get for this multiple choice exam, if I was asking about pure water versus black coffee, one of the wrong options would be 20. right? Because you might think, all right, it's 2 steps. Each step is times 10. So you might think 2 times 10, which is wrong, right? Yeah, I think that's the best example of the wrong answer you might get. So yeah, let me draw a little thing through this so you're not confused. 20 is not the answer. Another thing, so again, we know how to describe this as far as the numbers are concerned, right? Black coffee is, it's 100 times. And then here's the other part that you need to know is how to describe it. And again, there's different ways to describe it. It is 100 times less basic than water. It is 100 times more acidic than water. It has 100 times more H plus than water. It has 100 times fewer OH minus than water. See, I described this one situation in all those different ways, and that's how it's going to be on the exam. You're going to need to know at least one of those. So be familiar with all of them. Any questions about that? All right. This is funny. So there's a big thing where people try to scare you about chemistry, especially when they are ingredients in drinks and food and or vaccines. And one of the things people do to scare you about an ingredient is give you the chemical name for it instead of saying what it is. So dihydromonoxide is an acid with a pH level of 7. Well, first of all, it's all acidic, or it's all relative. So sure, we could say that it's an acid, and we could say that it's definitely.
I'm here. My bad. I cannot find your thing at all.
Okay. Well, we'll figure it out. Thanks. So, anyway, what this is really saying is water has a neutral pH, and that pH is higher than any acid, right? And based on what I just taught you, you'd be like, yeah, I know, I get that now. That makes sense. That's not scary, right? Because 7 is neutral, so we know that's not bad. And when we say it has a higher pH than any other acid, that's like, oh, okay, it's less acidic. But if you don't know what you're talking about, this might sound scary. Again, first of all, they used, instead of saying water, dihydrogen monoxide, right? The chemical name, how scary. And it's a higher pH level than any other acid, right? All that stuff sounds scary. And here's the thing, it's not even a lie, right? Everything on this slide is true. It's just meant to look scary. And people do this crap all the time. And this is one of the reasons why you need a basic understanding of science as a college-educated citizen. Not even that you would need to know this, but if you were to see this meme in real life, hopefully, instead of being like, oh my God, that's scary, hopefully you would just think right away, well, what is dihydrogen monoxide? What is that pH level of 7? Is it good or bad to be a higher pH level than any other acid, right? You should ask questions, but most people don't. Most people see something scary and they just accept it as scary and move on. Anyway, excuse me. Next thing we're talking about is buffers. This is a really simple concept. Buffers are just substances that minimize the change in pH. So, and you have a lot of them in your body. When you drink a margarita, if any of you are old enough to drink margaritas, it has a lot of, or how about orange juice? There we go. When you drink orange juice, that's pretty acidic. Citric acid is acidic. Hence the name. Yet your body, let me go back. Or here we go. When you drink black coffee or tomato juice or soft drinks, right? Your body doesn't change to those pHs, right? It would die. You would die if that happened. Your blood, what it doesn't show here is that your blood is right around 7.4. But if it gets too high or too low, and I mean like really close, like maybe, like that, if it changes, you die. So somehow you're able to drink coffee and juice and soft drinks without dying. That's because your body has buffers. And again, the main important thing you need to know for the exam is buffers are substances that minimize the change in pH. How's that happen? For the exam, that's a little bit less concern, but for your own knowledge, and hopefully you can figure this out. Matter of fact, I wish I would have asked you instead of showing you. When there's a lot of H plus ions, a buffer will accept it, right? So things aren't getting more acidic if you keep putting H plus ions in there and then something keeps taking them out, right? That keeps it from getting too acidic. Likewise, when things get really basic and you're missing H plus ions, these buffers are putting them in there, right? So again, it's hard to get too basic when something keeps putting H+ ions into the water. So any questions about buffers? Excuse me. I can feel myself getting worse as I'm sitting here with you. Your book points out that it's not foolproof. I'm not going to ask you any questions about this on the exam. Your book, or I think you have one question about it on the study guide, but your book gives the example of CO2, which is in the air, obviously, and we're having more and more of it from burning fossil fuels. That dissolves in seawater, and that forms an acid. So that acid obviously is going to lower the pH of the water, and that actually greatly changes marine environments. Specifically, the book example is coral. It kills the coral because you're making an acid, and coral is made up of something called calcium carbonate. So when you add acid to it, it basically dissolves it. But again, that's just an example. No need to know that for the exam. You will need to know it for the study guide, but that's it. We'll talk more about this concept later in the semester when we start talking about ecosystems and things like that. So any questions about that slide or the last two slides? All right. Again, every chapter has something called the evolution connection at the end of the chapter, and I will always skip it because it will never be on the exam. Now, this one's a kind of interesting one because it talks about how carbon-14, like carbon dating, and I'm sure you guys have heard of that. It tells you how that works. So, as always, I highly recommend reading it, and if you have questions, let me know. It is very interesting, in my opinion. So, let's go ahead and jump into chapter 3. And do we have any questions while I'm setting all this up? All right. We got about 20 minutes left. Let's see. I'm going to stop recording and then start again because technically that last video would be the end of chapter 2, and this next video will be the